students, and welcome to this next edition of the physics revision lectures. So today we are going to start the next section of our revision series from class 11 physics. We will look at the chapters of work by energy and circular motion. So let's begin. So let's start this section by just revising through the fundamentals of circular motion once. So for a particle or a body in a circular path or a circular trajectory, we know that by definition, if we define the origin of our coordinate system as the center of the circular trajectory, then the instantaneous position vector of such a particle which is in circular path remains constant with respect to time. So one very simple way of defining the circular motion is that it's a two-dimensional motion or motion in a two-dimensional plane such that at any instant the position vector of the particle has a fixed magnitude. Okay. And further we define what we call the angular parameters, where theta is what we call the angular position with respect to the x-axis. The change in angular position becomes what we call the angular displacement. Okay. And rate of change becomes what we call the angular velocity. And rate of change of angular velocity with respect to time, or second derivative of angular displacement with respect to time, that becomes what we call the angular acceleration. So this is how we define the angular parameters in a circular path. Okay. Now further on, we define the unit vector along the radial direction as our radial unit vector, generally denoted with r cap, and the unit vector along the tangential axis as our tangential unit vector, theta cap, you see. Okay, so the two important unit vectors in our vector notation become the radial and tangential unit vector. Which can be written in terms of the instantaneous angular position like this, and the tangential unit vector which can be written in terms of the instantaneous angular position as this. So you can see that they are mutually perpendicular. Okay. So having done this, now we can relate the kinematical parameters such as position, velocity, acceleration, etc. with respect to the angular parameters. Okay. These parameters together are called the angular parameters of the circular motion. And now we can define the kinematical parameters like position, velocity, displacement, etc. in terms of these angular parameters. So from the diagram, one can see that the position vector will simply be defined as the magnitude of the position vector, which is constant, into cos theta I cap plus sin theta j cap, where this is nothing but the radial unit vector. So it is nothing but the magnitude of the radius multiplied by the radial unit vector. Now we can define the velocity by calculating the rate of change of this. So thereby we see the simple relation that when we differentiate this term, it immediately shows us both the magnitude and the direction of the velocity vector. So completing the differentiation using the chain rule application, you can see it becomes this. But now we know that d theta by dt, the instantaneous rate of change of position, angular position with respect to time, is nothing but angular velocity. So this term further becomes this. Okay. So this gives us the important understanding here that the magnitude of velocity at any point of time is r into the magnitude of angular velocity, or the common relation between speed and angular speed. Okay. And the direction of the velocity vector is nothing but theta cap, which is the tangential unit vector. So it is tangential in direction. So with this, we are able to conclude that at any point during the circular path, just like the position vector has a direction along the radial line or along the radial unit vector, the velocity vector, the instantaneous velocity vector, will have a direction along the tangent to the circle, be along the tangential axis or along the tangential unit vector. So this is your radial direction, and this is our tangential direction. So the instantaneous velocity vector of our particle located at this particular position at this instant will be like this. Okay. And that's how it is related to the angular parameter of omega. So these two become important relations here. This and the fact that the direction of V is tangential. Next up, from the same logic, we look at the understanding of acceleration, which is rate of change of velocity with respect to time. We shall become rate of change of this term now. So with the understanding that omega is also instantaneous, it's an instantaneous quantity. So it may or may not have a rate of change, depending on whether omega is constant or not. And of course, we've seen earlier that theta is instantaneous. So we have to apply the product rule while doing the differentiation. So this becomes r into d omega by dt into minus sine theta I cap plus cos theta j cap multiplied by omega into differentiation of minus sin theta I cap plus cos theta j cap. So this becomes r into alpha into theta cap, and this term when we differentiate it, applying the chain rule again, we will get minus cos theta into d theta by dt, and then minus sin theta into d theta by dt. So this term therefore now becomes this, which we can see is the negative radial unit vector. So overall, we can now say that the acceleration is r alpha theta cap minus r omega square r cap. So this is the overall acceleration vector for us now. So we denote this as the sum of something called tangential acceleration plus something called the centripetal acceleration, where this is what we call the tangential component of acceleration, or simply the tangential acceleration. Okay. And is given by the relation r alpha, and its direction is the tangential unit vector. Okay. So I'll just leave you with a moment to go through this section. Right. So along with the tangential component of acceleration, the other component we have is called the centripetal component. Because it points towards the center. So that's what the term centripetal means. So the centripetal component is given by the relation minus r omega square r cap. So it has a magnitude of r omega square and points along minus r cap. Okay. So that is towards the center. So that is the meaning of this centripetal acceleration concept. So in context of this circular motion, you can see that the acceleration vector for the particular particle in concern overall in general would look something like this. If this is the instantaneous position for our particle at some instant of time, then the acceleration would have the two components, the tangential component pointing along the tangential direction and the centripetal component pointing along the centripetal direction. So this would have a magnitude of r omega square. This would have a magnitude of r alpha. And that means the net acceleration would be the vector sum of these two. So the net acceleration vector would be this. So this is about acceleration in circular motion in general. So the velocity is always tangential, but the acceleration will have a radial and a tangential component in general. But we'll also learn that in uniform circular motion, the tangential acceleration becomes zero because alpha is zero. Now, a few more points to understand about the acceleration. So this equation on its own implies that the magnitude of the acceleration will become square root of the sum of the squares of these two. Okay. Like this. First thing. Secondly, the magnitude of the centripetal acceleration can also be written as v square by r or v into omega, because we have this relation already. Whereas the magnitude of the tangential acceleration is r alpha, can also be written as r into rate of change of omega, which can also be written as dv by dt. So that means the tangential acceleration's magnitude equals to the rate of change of speed. So tangential acceleration equals to the rate of change of the speed, that is the magnitude of the velocity. So that's another important consequence of this derivation. Okay. And therefore we also understand that for a uniform circular motion, that is one where circular motion is happening at constant speed, so v is uniform. That means that omega is also uniform, because v is equal to r omega, which means that alpha is zero, which means that tangential acceleration is zero, because tangential acceleration is r alpha, or rate of change of speed. So uniform circular motion, so in UCM, uniform circular motion, the acceleration is just the centripetal acceleration. So these are all important properties of uniform circular motion. So this is about the kinematics of circular motion. Let's work out some questions based on this. For example, if we have a situation where we have a particle starts from rest on a circular track of radius 20 meters such that its speed v increases uniformly with time at the rate of say 3 meters per second square. So find speed v as a function of time. Then find its angular speed omega again as a function of time. Then find its angular acceleration alpha. Find the centripetal acceleration and tangential acceleration as a function of time. Find the magnitude of its acceleration A at t equal to, let us say, 2 seconds. So this is what we want to do in this question. Okay. So just give it a minute and try it out. We will discuss this question. Okay, so let us understand the solution of this question. So first of all, you can see that the information given to us that it starts from rest and that the speed increases with time at the rate of 3 meters per second square. So we know that initial speed is 0 and the rate of change of speed is 3 meters per second square uniform. So that will tell us here that okay, very simple thing, that as the time goes from 0 to t, the speed goes from u equal to 0 to some unknown speed v. So speed as a function of time becomes 3t meters per second, where t is time in seconds. Okay. So once we know the speed as a function of time, we know that okay, angular speed will become 3t divided by 20 because the radius was given to us as 20 meters. So the angular speed will become so much in radians per second at time t. So once we know the angular speed, now we know that the angular acceleration is nothing but rate of change of angular speed. So that becomes 3 by 20 or 0.15 radians per second square. This is uniform. That means my angular acceleration is not changing with time. That's about the angular acceleration. Now next we want to find out the centripetal and tangential acceleration. So centripetal acceleration's magnitude is omega square r, or b square by r, however you want to write it. So that is 3t by 20 whole square into 20. So that you can see will become 9t square by 20 in meters per second square. So centripetal acceleration is 9t square by 20, or we can say 0.45 t square in meters per second square. Whereas tangential acceleration is r alpha, or that's the same thing as rate of change of speed. So the tangential acceleration we will see will just become 3 meters per second square. It has a uniform value. Okay. So now we want to calculate the magnitude of acceleration at t equal to 2 seconds. So at t equal to 2 seconds, we can see that the centripetal acceleration will be 9 into 2 square divided by 20. So that's 9 by 5, or 1.8 meters per second square. Tangential acceleration is 3 meters per second square. So therefore, the magnitude of the net acceleration is just the vector sum's magnitude. So this is the magnitude of the net acceleration. It's something in the region of about 0.35. So 3.5, my mistake. Meters per second square. So this is an example of the application of this. Let's look at another example. So a particle in circular motion, okay, radius 10 meters, has a speed of v equal to 20 meters per second at an instant when its acceleration vector is at 37 degrees with respect to its velocity. So you want to find the tangential and centripetal acceleration at this instant, okay, and the angular velocity and angular acceleration at this same instant. So just give this question a try and we'll discuss about this also. Okay, so let us understand the angle that this particular question is talking about, that 37-degree angle. Let's try to understand that visually. So what it's saying that at some point of time in a circular motion, we can just assume some arbitrary time. The situation of the kinematical parameters, it is such that the instantaneous velocity and the instantaneous acceleration are making that kind of an angle. So let's just for variety say that the particle is here at this moment when this situation is happening. So it's over here at this particular point of time. Okay. In a circle of radius, I think we've taken it to be 10 meters. Yeah, in a radius of 10 meters, the instantaneous velocity is 20 meters per second at the instant when acceleration makes 37 degrees. Okay. So the velocity vector has a magnitude of 20 meters per second. So of course that's along the tangential direction. But also it is given to us that it is such that the instantaneous acceleration So this is what it means by saying that the acceleration vector is at 37 degrees with respect to the velocity at this particular moment. Okay. So the moment we see that, we can understand that the tangential component of the acceleration will become a cos 37. So that means r alpha will become 4 by 5e. This is our first equation. And the centripetal component of acceleration, which is pointing in this direction, we can see this is the centripetal, this is the tangential. So you can see the centripetal component is a sine 37. So centripetal component is v square by r in magnitude. So that is equal to 3 by 5 e. So we have this second equation. So from equation 2, we can see that 20 whole square divided by 10 is equal to 3 by 5 e. So the magnitude of acceleration is 5 by 3 into 40, or 200 by 3, or 66.67 meters per second square. This is the magnitude of the instantaneous acceleration. And therefore, the tangential acceleration, which is equal to r alpha, is 4 by 5 into 200 by 3. Is equal to this much. Okay. And once you got this information, all the other information like the value of omega and alpha, etc., can be derived from standard formulae. So we got the centripetal acceleration. So we can see the centripetal acceleration is 40. We can see the tangential acceleration is so much, therefore the net acceleration is so much. And we can see that from this relation, we know omega is 2 radians per second. And from this relation, we know alpha is so much. So this type of situation can also easily be worked out. Okay, so this is about our kinematics of circular motion type of situation. Now from here, next up, we move on to dynamics of circular motion. That is application of Newton's laws to circular motion. So the net force acting on a body when its mass is constant is mass into acceleration. So for a body in circular motion, for a particle or body in circular motion, you see that the acceleration is the sum of centripetal acceleration plus tangential acceleration. So what we do is the net force is also accordingly broken into components. So the net force acting on it has a centripetal component, which we can say is that centripetal force is equal to mass into centripetal acceleration. That becomes like this, and it has a tangential component. Like this. So this is what we solve in terms of vector algebra after breaking the force into components. So let's understand this with few examples. So let's take the case of a conical pendulum. Wherein we have a particle, let's say of a certain mass, attached to a light thread of length, certain amount, let's say. And this is now in sort of circular motion like this. In a circular path like this. So it's in a stable circular path with angular speed omega like this. So if the particle is in uniform circular motion, in a horizontal plane, as you can see, because gravity is acting along this line, such that theta is equal to 37 degrees. So you want to find omega and v for the particle, the speed and angular speed. And we want to find the tension T in the thread. So the second part becomes a dynamical question, and we need to calculate using the dynamics concept over here. So what we will do here is look at the free body diagram of the particle from the ground frame point of view. So from the ground frame point of view, what the particle is doing is it's in a circular path like this, which is a uniform circular path. So the forces acting on it are the tension in the thread and the gravitational pull that the earth is applying. This is the center of its circular path. It's going in a circle with angular speed omega about it. This is its radius. So this is the free body diagram. The thread will have a tension which acts like this. So two forces acting on the body in the inertial frame. So we can see that T cos theta has to balance the mg because the vertical acceleration is equal to 0. But T sine theta, that has to be equal to m omega square r. This is the centripetal force. You can see that by breaking tension into these two components, the sine component of tension here is the one which is providing the centripetal force. So these two become our important equations. Okay. Now geometrically you can see that of course r by L is equal to sine theta. So r by 5 meters is equal to sine 37, which is 3 by 5. So the radius of the circular path is 3 meters. Okay. So from equation 1, you can see that T into 4 by 5 is equal to the weight, which is 20 newtons. So the tension is becoming 25 newtons. Okay. And yeah, so the tension is becoming 25 newtons. And from equation 2, T into 3 by 5 is equal to 2 into omega square into 3. So we just saw that tension is 25. So we can see that omega is becoming square root of 5 by 2 radians per second. So the linear speed of the particle in the circular track is r omega, which is so much. So all the various parameters we have found out that we were required to. The angular speed, the linear speed, the tension in the string. By basically applying the Newton's second law concept, that what we've done is that net force is equal to mass into acceleration, and we've broken this into tangential, which in this case is 0, centripetal, which is T sine theta is m omega square r, and of course in this case this vertical, because the circular motion is happening in a horizontal plane where again the net force is 0. So that is the application of this particular question. Okay, let's look at another example of dynamics. So let's say this is some kind of a smooth hemispherical kind of surface. It has a radius of 10 meters. Now at some particular instant of time, we have a particle which is kind of sliding down this, and when it is at a position like this, that particle has a velocity that is known to us. So this particle, so particle P of mass 500 grams is at theta equal to 30 degrees at a speed of 6 meters per second at an instant, at a particular instant. So you want to find out its centripetal acceleration and tangential acceleration and the normal reaction contact force on the particle at this same instant. We want to find out both these parameters at the same instant. So once again, just give this a try for a moment, make the free body diagram of the question to try and understand this. I will explain this. Okay, so let's understand this question with a detailed free body diagram first. So at this particular moment, you can see that the forces acting on this body are going to be two in number, or rather the forces acting on the particle are going to be the weight vector, which is like this, and the normal reaction vector, which is like this. So when we are looking at it in the ground frame, there are these two forces acting on it. Okay. Now you can see that for its circular path, this is the tangential direction, and this is the radial direction, the direction in which normal reaction is acting. So now we'll have to break the weight into its components. So breaking up weight into components, the component of weight which is along the radial direction is mg cos theta, and the component of weight which is along the tangential direction is mg sin theta. So the centripetal force here, that is the force towards the center, is mg cos theta minus n, and that should be equal to mass into centripetal acceleration. So mg cos theta minus n should be equal to mv square by r. So that's our first equation. We know that the particle is moving with a certain velocity, certain speed v over here, which is given to us. Okay. And we can see that the tangential force, which in this case is mg sin theta, is equal to mass into tangential acceleration. So this becomes our second equation. Now it's a matter of solving these two equations. So we can see that from equation 1, we have mass was 500 grams, right? The instantaneous speed was 6 meters per second. Theta is 30 degrees and mass is 500 grams. So let's use those values. Okay. So from the first equation, we have, we'll take G as 10. So mg becomes 60 cos 30 degrees minus n is 60 into, oh sorry, mass is 0.5, my mistake. So the weight is 5 newtons. So 5 into cos 30 degrees minus n should become equal to 5 into v, which is 6, divided by r, which is 10. So the normal reaction should be so that's approximately 5 into So very nearly 2.5 newtons. That becomes a normal reaction. Okay. Whereas secondly, from equation 2, you can see that tangential acceleration is g sine theta. So the tangential acceleration of the particle is this much. The normal reaction acting is this much, and centripetal acceleration we've already seen. So these are the three answers. So I'll just leave you with a moment to go through this. We'll discuss the next question. Okay. So these are the basic type of questions at the dynamics level. And the next important thing to solve dynamical questions in circular motion is to understand the concept of writing the Newton's second law or solving Newton's second law while we are in a rotating frame. Just like earlier we had seen how to modify and write Newton's second law when we are in a non-inertial reference frame, which is accelerated with respect to ground. So like that, suppose we are in a reference frame which is rotating, and we want to make the free body diagram with respect to our reference frame, which is rotating with respect to the ground. Then what is the modification we have to make accordingly? So let's understand that. So just like we had seen that a body in a non-inertial frame experiences pseudo force, which is opposite to the acceleration. So we had seen from everyday life that when, for example, there's an object inside a vehicle which is having a horizontal acceleration, that object tends to experience a backward push, which is the pseudo force acting on it. Or if an object is in a vehicle that is moving horizontally, which brakes, so it's decelerating. So the object inside the vehicle tends to get pushed forwards because of pseudo force, which is opposite to the deceleration vector. So just like that, you can see in everyday life that when we are in a reference frame, or when an object or a body is in a reference frame that is rotating, like a person sitting inside a car which is taking a sharp bend in a circular path, that object or body tends to experience a force outwards, radially outwards. And that's a type of pseudo force which we call the centrifugal force. So any object or body or particle or whatever in a reference frame which is rotating, okay, with respect to the inertial ground frame, it experiences a type of pseudo force okay, called centrifugal force. Okay. And that centrifugal force points radially outwards, and it has a magnitude which is m into omega square into r, where m is mass of the body which is experiencing the centrifugal force. Omega is the angular speed of the rotating frame, and r is the radius, okay, of the body with respect to the axis of rotation. Okay. So let's understand this in context of dynamical situation. So for example, suppose we have a situation like this. This is like a disk which is spinning at a constant angular speed omega, and its surface is a rough surface, and there's a particle placed on it. At a perpendicular distance r from the axis. So particle P, mass m, is placed on a rotating platform as shown, okay, and does not slip with respect to the platform surface. Now we want to analyze the free body diagram. In the ground frame and in the rotating platforms frame. This is what we want to do here, this question. So through this, we'll understand the working of the centrifugal force as a pseudo force. Okay, so let's understand firstly in the ground frame, when we look at this, what is happening. So imagine an observer who is looking at this whole situation as an inertial observer from the inertial ground frame point of view. So what he sees is that according to him, the particle P is in uniform circular motion with angular speed omega and radius r about the axis. Okay, so in his frame, or angular speed omega naught or whatever, okay, and in his frame the forces acting on it are going to be its weight which is acting vertically downwards, a normal reaction force that the platform is applying vertically upwards, and most importantly there will be a frictional force which is providing the necessary centripetal acceleration. So there will be static frictional force which prevents that from slipping. So frictional force will be the centripetal force. So this static frictional force will be equal to mass into centripetal acceleration, whereas normal reaction and weight are cancelling each other, because okay, so what is happening here is that it's in uniform circular motion, so it has a centripetal acceleration of omega naught square r towards the center or the axis of rotation, and its tangential acceleration is 0. So that means the centripetal force has to be equal to m omega naught square r. The tangential force has to be 0, and the net vertical force also has to be 0, because it's a uniform circular motion in a horizontal plane, and gravity is perpendicular to the plane of motion. So this part is showing us that this is the case, okay, because the net vertical force is 0. And static friction is providing the centripetal acceleration. So another way to visualize this is, if this observer is seeing this from the top, he would understand it this way, that on that disk surface, the disk itself is rotating with angular speed omega naught. Now the particle is sitting somewhere here, so it's in a circular path of radius r. It's having an instantaneous speed like this. So in this diagram, you can see that this is the static friction, is the centripetal force. So he's basically saying that static friction provides the necessary centripetal force for the circular motion. This is the meaning of what we are doing over here. Now the same thing, when we look at it from the reference frame of the observer who's on that rotating platform, the situation is a little different. So now let us say our observer is actually on this rotating platform. So this is a rotating frame. So in that frame, the particle which is present will experience a centrifugal force. So it will be a force which is pointing radially outwards. Okay, this will be the centrifugal force, which is the so-called pseudo force for this particular frame. And apart from this, of course, there is static friction acting like this, and weight and normal reaction balancing each other by acting like this. So with respect to this rotating frame, you can see the particle P is at rest. Which means it's in equilibrium. Net force on it should be 0 in the rotating frame. Okay. So that's happening in such a way because static friction balances the centrifugal force. So static friction balances the centrifugal force. And of course, normal reaction balances Ng. So same thing when you're looking at this from the top view, But now, because you're part of the rotating frame as an observer, you're not seeing the object in going in circular motion. You are part of this frame. So in your frame, the object is at rest. So it's at rest because the centrifugal force acting on it is balanced by the static friction. So it remains at rest. And of course, normal reaction and weight are balancing each other. So this is the understanding of centrifugal force for an object in a non-inertial or in a rotating frame, as be the case over here. Okay. So this becomes a necessary tool for solving the more complex type of questions of circular motion. So we'll take an example of such a problem. So this is, let's say, a hemispherical surface. It's a hemispherical bowl rotating at uniform angular speed, omega naught, as you can see. Okay. Now inside this, what we are observing is that there is a particle which is at an angular position like this. And this is a rough surface. So a particle P of mass m is at theta equal to 53 degrees with respect to the vertical axis of rotation. Okay, and does not slip with respect to the rough inner surface of the bowl. So this hemispherical bowl itself is, let's say, of radius capital R. So suppose given that R is equal to 10 meters, G is equal to 10 meters per second square, and omega naught is equal to 4 radians per second square. R is not that much, let's say R is 20 centimeters. You want to find the frictional force and normal reaction on the particle, and we want to find the minimum value of coefficient of static friction so that this condition is satisfied. So just take a moment to go through the question and maybe try out making the free body diagram yourself, and next we'll discuss how to solve this problem. Okay, so the easy way to solve this problem would be to understand the equilibrium of the particle in the rotating frame. So, if we take that into account, that with respect to the rotating Bole's frame, okay, the particle P is in equilibrium. So the moment we understand this, it becomes very easy to solve because we have to just balance the forces. But of course, to execute this correctly, we have to also be able to apply the centrifugal force concept correctly. So let's see how that works out. Okay. So what is happening is that with respect to this frame now, you can see that the particle should be at rest in the rotating frame. But at the same time, it's at a radial distance like this with respect to the axis of rotation. So this is its radial distance. Okay. So in this rotating frame now, which is going around with an angular speed omega naught, the forces acting on the particle will include centrifugal force, which will act in this direction. Then the other forces like gravitational force and the normal contact force, which will act like this. So normal reaction is there, mg is there, and most importantly, centrifugal force is there, which will have a magnitude of m omega naught square small r. Now you can see that small r will become capital R sine theta. And we can see that this angle is theta. So I can see that this angle is theta. So now, according to the values given, you can see that this is becoming 20 centimeters into sine 53. So 16 centimeters or 0.16 meters. Okay. So our centrifugal force will become m into, now omega naught was given to us as 4 radians per second. This will be our centrifugal force. So you can obviously see that an mg is m into 10. Okay. So you can definitely see that mg's sine theta component is much larger than the centrifugal force's cos theta component. So this is only 2.56 times m and this is 10 m. And theta is anyway such that sine theta is greater than cos theta. Okay. So the particle has a tendency to slip down the surface because mg sine theta will be dominating. So static friction, this has to act up the surface. So that will now justify the next thing I'm showing, that the direction of static friction in this diagram will be like this, along this direction. Okay. So in a moment, I'll make a more detailed diagram of this with the forces resolved and all that. Okay. So with the forces resolved, you can see that centrifugal forces components will become cos component, sine component. Okay. Then mg's components, sine component, cos component. Then we have normal reaction. Okay. And to help it from not slipping, we have static friction. So this is the resolved forces over here. Okay. So given that in this frame, this should be at rest, it should be in equilibrium, so forces should balance. So we have the relation that normal reaction balances mg cos theta plus centrifugal forces sine component. So that is so that becomes our normal reaction. So this will become approximately 8.05 m, whatever the mass is. That will be our normal reaction force. And next, from the radial direction, from the tangential direction to the surface, we can see that mg sine theta is balanced by the combination of static friction plus centrifugal forces cos theta component. This is our second equation. So the first equation. So let us solve this now. So this will tell us that static friction is mg sine theta minus m omega naught square r cos theta. So this will come out to be m into 8 minus 2.56 into 0.6. So let's see how much that is. 1.54 approximately. This is approximately 6.46 m. This is the static friction. And now connecting these two, we can see the limiting value of μs needed. So static friction should not exceed its limiting value. So 6.46 m should be less than equal to coefficient of static friction into 8.05 m. So that means we require a coefficient of static friction which is greater than equal to or approximately 0.80. So this is the limiting value of the coefficient of static friction finally. So this is an example of a complex type of dynamical problem. But again, you can see that the application of centrifugal force and analysis in rotating frame is making it somewhat simpler. And the complexity is really more about the limiting friction aspect rather than the dynamics of circular motion. So hope this session is clear. Make sure to revise the derivations of centripetal and tangential acceleration concept, the kinematics of circular motion, and then understand the applications of the same when it comes to dynamical problems. So in the next session, we will pick up work energy theorem, and we will look at a lot of applications of conservation of mechanical energy or work energy theorem applications, etc. Concept of conservative and non-conservative forces in detail. And then towards the end, we will come back to circular motion, but with application of work by energy, where we'll understand, for example, in cases of vertical circular motion, how to incorporate conservation of mechanical energy or work energy relation to do the calculations apart from the dynamical equations. Okay. So hope you have enjoyed today's session and wish you all the very best. That's it for today.